is not there.
Yeah, it says now it's being live streamed.
That's good.
Yeah, so I think it's going live now.
IIT Madras.
Probably I'll also turn the video off.
Please keep your mic switched off. For the
NIR. NIT राउरकेला भी है मैं 8वीं रैंक पर रिसर्च कमेटी
I don't know my please keep your mics.
जैसे उसमें भी उन्होंने अलग-अलग कैटेगरी डाली है तो रिसर्च में IIT मद्रास है
Sujata Mishra, please. Sujata Mishra, Sanjul Mishra, please switch off your mics for the talk so that we can start. Please keep your mics switched off. Yeah. So I think it's time to start. It's my pleasure to welcome Dr. Venkata Balaji from IIT Madras to our humble effort of Math Clinic. Professor Balaji is a faculty member at IIT Madras. His expertise is in complex algebraic geometry and moduli spaces. Other than doing teaching and research at IIT Madras Maths department, he is also very much contributing in NPTEL video courses to make mathematics available to people outside IIT. So with this very short introduction, let me request Professor Balaji to start.
Thank you, Professor Rana. It's a great pleasure and honor to give talk here in your math clinic, which I see is it's a very nice effort on your part to make mathematics enjoyable and down to earth, and to encourage and inspire people who would like to either learn or do research or teach mathematics. I saw several of your earlier videos, and it was quite inspiring to see interesting talks. So yeah, so thank you for this opportunity. So I'll go ahead and share my screen,
please.
Yeah, so I hope I'm audible. Am I audible?
Yeah, you're audible. Your
Yes,
screen
sir.
is visible. Please go ahead.
Yeah, okay. So so you see, so the aim of this talk is to concentrate or try to understand in a, let's say, a nicer way one of the most important things that we do when we do mathematics, and that is these are the definitions. Okay, and I often remember an acquaintance of mine who used to say a good definition is worth 1,000 theorems. And so, a definition is very, very important. And usually the way the theory goes is that, you have usually the buildup of a theory is like this. You have the so-called axioms. And and after the axioms, you have the definitions. And from the definitions, you prove, various results. You prove first some lemmas, and then, well, there's a hierarchy, then propositions, and then, you prove theorems. And, well, and the theorems are the, if you want, the pinnacle of results that you have, that you can prove. And of course, what is to be called as a lemma or a proposition, what is to be called as a theorem is it can be somewhat controversial. So I usually when I teach, I say that lemmas are the ammas of theorems, and that's because there are certain lemmas which are so beautiful and fundamental that if you understand them, essentially, then you understand the whole theorem. Sometimes, in a way, if there is one point of view where you think of lemmas as small bits of deductions, and then there is another extreme viewpoint where certain lemmas are extremely crucial. But usually the simpler ones are called lemmas, and the what you build from the lemmas are called propositions, and then you get theorems. So you see, the axioms are a certain set of given principles or rules that you start with. Okay, you say that things should behave in a certain way. Okay, so the axioms are kind of given. Now the point is that you make definitions, and then the of course the aim is you make definitions, and then you see what is it that you're going to get out of a definition. And of course, definitions are inspired by examples, usually, of certain phenomena that happen. And then you look at some phenomenon, you see that there's some property that you can prove about it, or you see about it, and then you isolate that property and make a definition out of it. And then the question is that abstractly from that definition, what consequences can you get? Okay, so that's the usual way mathematics progresses. So you see, I want to just tell you that so you see the importance of the whole the whole structure here is this step of making definitions. So of course one can get into a kind of meta-mathematical or philosophical kind of mathematical philosophical question as to when can you say that a definition is really a definition? Okay, which is like, what is a good definition? Okay, so you can ask this condition, or you can ask this this question. Ask for conditions if you want. What is a good definition?
Professor Balaji.
Yeah.
There is a request that can you enlarge your they're not
my handwriting, is it too small?
Yeah, it looks like some people are requesting if you can zoom a bit somehow. Yeah, that's good. That's good enough.
That's good enough. Okay.
So, yeah, I think that's good enough.
Yeah, I can zoom the screen. Yeah, I'll do that.
That's okay.
Yeah, sure. Yeah, please, if anybody is having any difficulty, please do give feedback, and I can correct that immediately. Yeah, thanks. Yeah. So the question is, what is a good definition? Or is there some way, is there some nice way that you can always make good definitions? Okay. Is there, a nice way, so I put it in quotes, to make good definitions? Okay. And of course, these questions are very, very important, because many a time understanding a definition itself is a task for students and for first learners, and even for people who know when new definitions are given, there's a lot of analysis that has to be understood. So certain questions that normally I ask students, or even myself do, is that when you look at a definition, you ask why is this definition being made? Okay, and usually the answer is that once you make these definitions, so I believe somebody has not muted their mic. So I request all participants to mute their mics.
Balaji, are you able to say something?
Yeah, Professor Balaji, you need to unmute.
Somehow the video, this video has it says, is my screen visible?
Yes, screen is visible but not video. If
yeah,
possible.
now it's okay.
Now, can you see it? Because when I went to the Zoom app, it says that the video somehow is cut off. There is a red strikeout on the video logo, but it says you are sharing the screen. So I assume that therefore, since I'm sharing the screen, it's not allowing me to switch off my video. But my screen is visible, right?
Yeah, everything is okay. Please go ahead.
Yeah. So the one of the questions that one can ask is that, why should you make a definition? And so the usual answer to that question is that, after you make these definitions or a definition, you give some examples to show how such a thing, there are objects which satisfy the definition. And then these objects have certain newer properties, which is what, these lemmas and propositions and theorems establish. And therefore, at the end, the proof of the pudding is in the eating. So you're happy that you made that definition. But more generally, making definitions, making good definitions and understanding why they are made, that at the fundamental level itself is a question. So what I'm going to do is I'm going to illustrate this by giving an answer to this question here, that is there a nice way to make a definition? Okay, and the answer is yes. The answer is by using a definition which involves what is called a universal property. Okay, so let me write down the answer. Yes, there is a nice way if you can find a way to make the definition using what is called a universal property. So, so what is this business of a universal property? So what is the universe that is being referred to? So the universe that is being referred to is what is what is called a category. Okay. So this universal is relative to a category of objects. So I will not get into the the nitty-gritty of defining a category and things like that, but I can tell it to you in a very, very naive way. Okay, so what is a category? See, when we look at objects in mathematics, they are objects with a certain structure. Okay, so you have groups, you have, if you want, rings, then you have vector spaces, you have topological spaces, there are fields, and so on. And then there are these objects of a certain type that you want to study, but you see, just looking at objects of a certain type is of no use, because you also have this very fundamental classification question. Namely, if I give you two objects of the same type, when are you going to decide that they are literally the same? Okay, and when can you say that they are not the same? Okay. So that you have to compare objects, and the way to compare objects is that you need communication between these objects. Okay, and these communications are given by what are called as morphisms, which are in the case of objects which are actually structures on sets. These are actually maps going from one object to the other, and they are also supposed to preserve the structure. So, for example, if you have two groups, communication would be an arrow, a map from one group to the other, and it has to be a group homomorphism. It has to respect the group structure. Okay, and similarly, if you have two rings, you have a ring homomorphism. If you have two vector spaces, you have a linear map. Okay, over the field over which you are considering the vector spaces. Okay, and if these are two topological spaces, then the map is a continuous map. So the big deal is that you need these arrows which are communicating between the objects, which go from one object to another. Okay, and then comes this definition that two objects are the same if they are what is called as isomorphic. And isomorphic means that there are two arrows in the two opposite directions, such that the compositions are identical. Okay, which is what you normally have even if you have a bijection, okay, of two sets. So the point I want to say is that there's no use of just studying objects. of a certain type, you need to also compare them, and the comparison is done by considering two objects equal if they are isomorphic, and that means you need an isomorphism between them. But an isomorphism is two arrows in opposite directions whose compositions are identity. So basically, you can't do without arrows. And so you see, this is the idea of a category. It's not just objects, you also need the arrows between the objects. So in some sense, category is not just studying objects of a particular type. In fact, it is actually studying arrows. So that is the point of view I want you to understand. So when we say we are working in the category of groups, what it means is that the objects are groups, and the arrows of the category are group homomorphisms. And similarly, when you're working in the category of, let's say, vector spaces over a field, and the objects are, of course, vector spaces over the field, but the arrows are the linear maps from the linear transformations, okay, from one vector space to another over the field, okay, and so on and so forth. So you see, so I want to just briefly say that this is the idea of category. So it's just a category of objects, but let me write it here. Category, it has the data of objects, and there are the so-called morphisms, okay, and the objects are usually given by letters, capital letters like this, and morphisms are usually thought of as maps, which are like arrows, which are given by the small f going from the object A to the object B, okay. So the category, I wanted to think of category as basically these two pieces of data, okay. All right, so now the idea is that this universal property is relative to a category of objects, and so what it is something that let me motivate this by giving you certain examples so that you see what a universal property is. And at the end of the talk, I want to convince you that if you have a good definition, okay, the first thing we should do is try to see whether it comes from a universal property, and if it does, then your definition is excellent, okay. So that is the conviction I want to give you, okay. So let me begin with some examples. So I'll start with let me start with but before that, let me say, you see, this universal property is actually a property of arrows, okay. It's a property of arrows, and you can as well call it as arrow theory if you want, okay. And what I want to say is that this universality is actually the power of arrows. So that is exactly the thing that's going to happen, as you are going to see. So let me start with with these. There are two examples I have given in the abstract for the talk. One is the polynomial ring, the familiar polynomial ring in so many variables, if you want, over a field, okay, the ring of polynomials. And then the other familiar example is that basis of a vector space, okay. So let me get into that. So let me start with the simplest thing that I can go is is to the category of groups. So let me start with groups. So you see, so there are several things about groups that we normally learn. So if you take two groups G1 and G2, and you take F, a group homomorphism, then so we have connected with this group homomorphism, there are the fundamental isomorphism theorems which give very nice decomposition of this arrow. So what you have is that so let me write it in the so-called category theoretic way. So you have this group homomorphism F. Then what you have is that for the F you have this kernel. There's a kernel of F. And what is a kernel of F? Of course, the kernel of F is all the elements in the first group such that they are mapped to the identity element in the second group. So G2, E1 is the identity element in G1, and E2 is the identity element in G2, okay. And kernel F is all the elements in small G1 in capital G1, which are mapped to E2. Okay, so that is the kernel, and we all know that this kernel is a normal subgroup of G1, and then you have you can divide by a normal subgroup to get a quotient. So you have G1 mod kernel, you have this quotient. So you see this, you have this. So I put this triangle here. So actually, there's an inclusion map. This is kernel F being thought of as subset of G1, and this is this double arrowhead here is supposed to indicate quotient surjective map, and this is the quotient. This is the quotient group G1 modulo the kernel. Okay, and so you have this decomposition. And as far as the target group G2 is concerned, what you have is that you have the so-called image of F, okay? And the image of F is just F of G1, and that is a subgroup of G2, okay? So you have this thing, and of course, these two are isomorphic. The source group divided by the kernel is isomorphic to the image, which is subgroup of the target. Okay, so this is the fundamental thing that we normally look at. And now what I want to tell you is that each of these things that we see here, the kernel of a homomorphism, okay, and this is a quotient, okay, and this is an image, okay. So the point I want you to understand is that F is a homomorphism. It's an arrow, okay. It's an arrow in the category of groups, okay. It's an arrow from G1 to G2. Okay, it's a group homomorphism. But related to this arrow, you're getting these objects. You have kernel, then you have the quotient, then you have the image. Okay, and of course, if this image was actually a normal subgroup of the target, I could have gone and put a quotient here. So let me put that in. I'll put it in dotted arrows to tell you that this needs a condition. So I can put a dotted arrow like this, okay, and I can get a quotient G2 mod F of G1, and this is provided, I can do this provided that F of G1, is normal subgroup of G2, okay. So because you can only divide by a normal subgroup to get a quotient group, okay. Otherwise, if you divide by just a subgroup, you only get a coset space of either left cosets or right cosets. So you can get this arrow also, and this has a special name. This is what is called as co-kernel. This is called the co-kernel. It is the target, which is target of the morphism, which is G2, divided by the image of the morphism, okay, which is FG1. So it's called the co-kernel of F. So basically, there is this very beautiful way of breaking down any arrow into a kernel, a quotient, an image, and a co-kernel, okay. And of course, the co-kernel part is, it involves something. For example, if the target group is abelian, okay, then every subgroup is normal. So co-kernel is defined. Or more generally, if you're only working with abelian groups, okay, or with kind of linear objects, then you can always divide. So, for example, if you are looking at modules over a ring, say left modules or right modules, or if you are looking at vector space over a field. Okay, in all these cases, you can always divide to get a quotient object. Okay, so this is a situation. But I want to draw your attention to the following thing. You see, we started with a morphism F. Okay, it's an arrow, but connected with this arrow, I am getting all these these objects. I'm getting the kernel, then I'm getting the quotient, then I'm getting the image. And if the image is normal, then I'm getting this co-kernel here. Okay. Now, so if you want some kind of uniformity, okay, it is possible to think of these objects, associated to F, namely the kernel, the quotient, the image, the co-kernel. You can think of them also as arrows. So you see, here is so this is why I'm insisting on what is called as arrow theory. So you see, trying to transfer everything to arrows, okay, to try to transfer all your definitions to arrows. That is one of the importances of category theory. And the advantage of that is that you can actually sometimes do away with working with elements, okay, and get properties. Okay, so I'll try to explain that. So what I'm going to do is, so let me give you an example as to how to get the kernel, okay, of a morphism, which a kernel of an arrow also has an arrow, okay. And so the arrow that I'm talking about is actually this one. So so you see the arrow I'm talking about is this one here. Okay, so let's try to understand that. So this is just an instructive exercise that you can try on other things. Okay, so let's look at this. You have G1, then you have G2, then you have F, then you have this kernel of F. Okay, and this kernel of F is sitting inside here. Okay, and this so this hook arrow is supposed to denote an injective map, okay, because this is just a subset. This is the natural inclusion. If I want, I'll call it as I, okay. And what are the properties of this I? You can see that. So the first thing you can see is that because this is a kernel, if I compose I with F, I will get the trivial map. So you see, if I take first apply I, then I apply F, this will be the trivial map. This is the trivial or constant homomorphism. And that's obvious because F of I of any if you take any G1 in the kernel, F of I of G1 is going to be I of G1 is just G1. The F of G1 is going to be E2 because this G1 is in the kernel for G1 in the kernel. So you see, the composite map is a trivial homomorphism. It's a trivial homomorphism from this kernel, which is subgroup of G1 to G2. Okay, so that is one property. So these are, so I'm just looking at the properties of the kernel. Okay, so this is the first property. Then here is the second property. The second property is, of course, suppose there is a map from G1 to, let us say, G2 prime, and suppose I call it as F prime. And suppose this also has the property that if I compose this I with this F prime, I still get the constant homomorphism. Okay, then what does it mean? It means that the elements of the kernel of F are also going to go to the trivial element in G2 prime under F prime. That means kernel F has to be contained in the kernel of F prime. Okay, and therefore you see so the moral of the story is you can now say that so let me write this here. Or rather, so this is not what I wanted. Just hold on. So I want it the other way. Yeah. So whatever I was saying is, it's not a dead end. Actually, that is the thing that you have to look at if you want to define the image. But let me not get into that. So look at this. So I'm trying to characterize this. I'm trying to characterize the kernel. Okay. So and I'm looking at the kernel as the kernel, which is actually a subgroup of G1. I'm trying to see it as an arrow. And what is the arrow? So the arrow, if it's a morphism, it has to go from something to something. So the arrow I'm taking is the inclusion map of the kernel into G1. Okay, and I'm studying this arrow I. Okay, and then I see that I composed with F is a trivial homomorphism. Okay, and here is a beautiful thing. Suppose I take some other arrow. So suppose H is a group, and suppose I take an arrow like this. Okay, suppose that I take J, another arrow from H to G, with the same property that if you compose H with this arrow from H to G1 with F, so which is first apply J, then apply F. Suppose this is a trivial homomorphism. Okay, suppose this happens. So this is such that F circle J is trivial. Then what happens is that you see, of course, mind you, whenever I write an arrow, it has to be a homomorphism. Okay, because I'm now in the category of groups. So every arrow that I'm putting is a homomorphism. Okay, so it's a group homomorphism. So J is a group homomorphism from the group H to group G1, and it has this property that F circle J is trivial. Okay. Then what happens? So you see, then you can see the the image of H under J has to go and fall inside this kernel. Okay, so you see what happens is that you get a map. The H has to, the image of H under J has to go into the kernel. So what you get is you get a map like this. Get J1 from H to kernel F such that this diagram commutes. Namely, what is the meaning of saying that the image of H under J lands inside kernel F? It means that you can this J is actually landing inside kernel F. Okay, but if J lands inside kernel F, I can't still call it J because now a morphism is completely, the name for a morphism, it depends on the source and target. Okay, this map J, this morphism J is from H to G1, but it lands inside kernel. I can't still call it as J because J target should be G1. So that's why I call it as J1. J1 is literally J. What I mean by that is element-wise, J1 is exactly the same as J. Okay, but the point is J1 is actually the map that lands in the kernel. Okay, and what is the circular arrow I have drawn here? It is what is called as a commutative diagram. Namely, all I'm saying is that J1 followed by I is J. So this circular arrow means that this J1 followed by I is actually J. That is the meaning of this circular arrow here. Okay, so here is so what is happening? So you see this kernel has this property that it is an I which composed with F is it gives you the trivial homomorphism. That is the first property. And here is the second property. Given any other J which composed with F is trivial, you are able to get a unique. So there exists a unique arrow J1 from H to kernel F, such that this thing happens. That is J1 factors through. J factors through J1. It factors through I. So the J1 circle I is J. Okay, and so these are two properties that are quite obvious. And then you have two more properties, and let me write them down. The third one is this I. So kernel F, this I to G1 is injective, because after all this is a subgroup. Okay, so there's an injective map. Okay, and then you also have the fourth thing, namely the image of kernel F under I, which is just kernel F, is actually a normal subgroup. So there is a quotient. So the point is that I kernel F to G has a quotient, and this is the same as saying that a kernel F, I of kernel F is a normal subgroup of G. Okay, because unless you have a normal subgroup, you cannot take a quotient. So you see that these are the four properties that you can see for the kernel. And now comes the very beautiful thing. Okay, what is amazing is that these two properties, they are good enough to give a definition of the kernel as a arrow. Okay, with a universal property. Okay, so now this is the motivation for the definition. So here is so let me make the definition here. So here is the definition. So the definition is a kernel for F from G1 to G2 is a homomorphism. So let me write as K some J into G1. It's a homomorphism to G1 such that, okay, so I'm just going to use these two properties, okay, which the usual kernel has. So such that, number one, if you compose this J with this F, you should get the trivial map. Okay, so let me write it. K to G1 to G2, this is F, this is J, this is the composition. So I put a circular arrow here. That means this is first apply J, then apply F. This is the trivial map. Trivial map means constant homomorphs. Okay, everything mapped to the identity. Okay, this is the first. This is the first thing, and this was this property that we saw above here. Okay, this one here. Okay, now and then there is a second property that I'm going to use in my definition. So number 2, if whenever you have H to G1 H, okay, such that the composition is trivial map H to G1 to G2 F, the composition is going to be, of course, first apply H, then apply F. F circle H is a trivial map. So here is the statement. So let me draw a picture here. So you have already K to G1 to G2. This is your F. This is your J. Okay. Then I am now given a H, which is small h from capital H to G1. Now with this property that H followed by F, this is trivial. Okay. And of course, J followed by F is also trivial. That is already property 1. Then the point is that, this map factors through K. So there exists a unique H tilde. So this arrow here is H tilde. So let me write it correctly. Such that this diagram commits. So you see so let me write it here. There exists a unique H tilde such that you first apply H tilde and then you apply J, then you get H. So it's like, to put it in simple words, this kernel, if you take this morphism F, okay, the kernel is this J with the first property that if you take J followed by F, you'll get trivial map. And whenever there is some other H such that H followed by F is a trivial map, then that H has to factor through this J. So that is the universal property of the kernel. So you see, this is so what I have done is I have made this definition. I'm saying that a kernel for a morphism is another morphism with these properties. And now this is an example. This is an example of what is called a universal property. Okay, and why is this universal? And so why is this a good definition? Okay, so see, the first thing I want to say is that of course, this definition, it was motivated by looking at the kernel of F. Okay, so actually the motivation was, for capital K, you take kernel kernel of F, which is a normal subgroup of G1, and J is the natural inclusion of that kernel in G1. Okay, that was the motivation. Okay, but suppose you forget that. Okay, and look at this definition. The beautiful thing is that this definition is extremely powerful. Okay, and so these 1 and 2 together are called the universal property of the kernel. Why are they called the universal property of the kernel? Because the universal property ensures that your definition is good. What does that mean? It means that, if there are 2 candidates which satisfy the definition, then they are uniquely isomorphic. So you see, one of the obvious things about a definition is that it should really define something. And what does define mean? It should give it unambiguously. So a definition should not give rise to 2 objects, okay, which are different from each other. And what is said in another way, if a definition is satisfied, the good definition is satisfied by 2 objects, they have to be the same. But what does same mean in category theory? It means that they are isomorphic. So the big deal is that, when you put these 2 conditions, okay, and define a kernel, then it automatically follows that any 2 kernels are isomorphic, and that is the beauty. Okay, so let me prove that. So just to tell you the power of arrows. Okay, so and you see, there are several other things that are kind of hidden. Okay, So which also I will point out. So you see, in this definition, there are several other things that I didn't, which I have not put into the definition. So for example, when we looked at the kernel of a homomorphism, we had also these things. The kernel, the map from the kernel to the group is actually injective. Okay, the kernel is actually a subgroup. Not only that, it's actually a normal subgroup because you can divide by it to get a quotient. Okay, so these two things are not there in my definition. So you see, what you must understand is that in my definition, this J, I'm not saying J is injective. Okay, I'm not saying that. J is just a map. It's just a group homomorphism satisfying these properties. And then I'm also not saying that, the image of J, the image of K under J, the image of J, that's a normal subgroup of G1, I'm not saying, but it will happen. So you see, this is the power of this definition. Okay, that the J has to be injective, that the image of J is a normal subgroup of G1. Okay, all that is already buried in this definition. So that is the power of the universal property. So first of all, let me explain why, why this definition is good. Okay, so so towards that end, so let me do it. So I'm changing colors just for some visual appeal and some relaxation to your eyes. But if there's some color that's not coming out correctly or something is not easily readable, please alert me. Okay. So so here is the first lemma. So the first lemma is, any two kernels are the same. That is isomorphic. Okay. And so you see, this is one important property of a definition. If the definition is good, if there are two candidates for the definition, okay, then they should be isomorphic. Otherwise, the definition is bad. A definition should not give you two objects which are grossly different, okay, which are different, which are not isomorphic. So why is this true? So so let me write this down. It's pretty easy. But you see, this is actually, this is the part of mathematics where arrow theory, category theory, where people just fiddle. They just tinker with arrows, and with arrows you're able to prove everything. And most of the time you never work with elements at all. Okay, and you never consider elements and make calculations. You make calculations only using arrows. And you may ask, why is this beautiful? Of course, what I'm trying to tell you is that this kind of arrow theory is useful to define universal properties that makes good definitions. That's one part of the story. There's another part of the story in abstract mathematics where all your mathematical objects, see, they need not be as simple as we normally encounter them. See, normally our mathematical objects are sets with some extra structure. Therefore, a morphism from a set with a structure to another set with a structure is at least a set theoretic map. And since it's a set theoretic map, you can work with elements. But you see, in category theory, the objects can be more complicated than sets. And therefore, they need not be sets at all. Okay. And then if the objects are not sets at all, then you cannot think of an arrow from one object to another as a set theoretic map. But the point is, still you can make sense of arrows. So you can have arrows and objects which are not sets, and arrows which are not set theoretic maps. But still you can make these universal properties, you can make these definitions, and all arrow theoretic proofs will still go through. Okay, so that is the power of category theory. Okay, you don't have to worry about whether elements are there or not. You only isolate arrow theoretic properties, and giving a universal property is one such application. Okay, so let me get back. So you see, you have suppose. So let me give the proof here. Okay, and I'm writing this proof instructively so that you realize what is involved. So suppose K1 J1 to G1 and K2 J2 to G2 are two kernels of two kernels of
Excuse me, sir.
Yeah, tell me.
So that should be G1, right? J2 map. The target of J2 map should be G1.
Oh, sorry. Yeah, that should be G1. Yes. Thank you for alerting me. Yeah. Both of them have, both of them should have target G1. That's right. Two, yeah, thanks. Yeah. Two kernels of G1, two G2, two kernels of F. Okay. And now you see, so let's do this. So you see, you have K1, you have J1, and this is G1, this is F, and this is G2. Okay. Then you have this K2, and you have this J2. Okay. And of course, since K1, K1, J1 is a kernel, so this is this composition is trivial. Okay, and you see, on the other hand, K2, J2 is also kernel. This is also trivial. Okay, now you see this K1, J1, this satisfies those two properties. Therefore, you see what happens is that, you know, since J2 followed by F is trivial, this J2 has to factor through J1. So, you know, there exists a unique map. Okay, let me call this as so I think this was J2 tilde, such that this diagram comes. Okay, and then so here what have I done is I am using so I will not say universal property. I'm saying using the property of the kernel, which is K1 to G1, okay, which is J1, okay. And now do the same thing with K2, okay. So by the way, the fact that, you know, this diagram commutes means what? You apply J2 tilde, then you apply J1, okay, you should get J2. That's what it means, okay. Now let me do this with K2. So you see, you have K2, J2 from K2 to G1, and then you have F into G2. This is trivial, and this is a kernel. And you now take this, put the K1 below, and you know K1 to J1 you have this map, and this composition is trivial. Okay. Now because K2 J2 is it satisfies the properties of the kernel. What will happen is that you'll get a map like this. Now this time the map will be from K1 to K2. Mind you, this J2 was from K2 to K1, J2 tilde. Now you'll have from K1 to K2, you'll have J1 tilde. So you'll get a, there exists a unique map like this. Okay, and this is what here you're using, the universal the property of the kernel K2 J2 to G1. Okay, and again, what does this commutativity of this diagram mean? Here it means that you apply J1 tilde, then you apply J2, then you will get J1, and now you put these two things together. Okay, substitute this J1 value here, and what you will get is that you will get J2 circle J1 tilde circle J2 tilde is equal to J2. Okay, and so if you look at it, so if you group this, because composition of maps is associative, you can write as J2 circle J1 tilde circle J2 tilde is equal to J2. Okay, so now you have to be, and now there's a little bit of a there's a thought that there is some subtlety here. So let me say this. So you see, this J2 is a map from where to where? It's from both these maps are from K2 to to G1. So you have, so let me write this. So K2 to G1, you have this J2, okay, and there is this F, of course, okay, and then here I have K2 to G1. I put the same J2, okay, and this is trivial and this is trivial, okay, of course. After all, I've written the same thing above and below, okay, and by universal property, I mean, I keep saying universal property, but because it's going to be the universal property, I mean, these two properties that define the kernel, what happens is, there is only one map that exists. So you see this, why do I keep saying that there exists unique? See, this uniqueness is going to really play a game here. There exists exactly one map here. If you want, I call it as J2 tilde, J2 hat, okay, such that this diagram comes, okay. And what does this mean? So here, what am I doing? See, I am applying the property of the kernel to the kernel itself, okay. I'm applying the property of the kernel K2J2 to the kernel K2J2 itself, and I'm getting this J2 hat. And what does the commutativity of this diagram tell you? It means that you apply J2 hat, okay, then you follow it by J2 is equal to J2. That's what it means. And mind you, there exists unique is important. There's only one map from K2 to K2 that does that. But there is one map for which it obviously happens, is identity map. So we have, you see, also obviously J2 circle, if you put identity on K2, that will also be J2, of course, right? Because, identity followed by anything is the same thing, okay? So the fact that this J2 hat is unique will tell you that this J2 has to be identity on K2. You should, that's what I wanted to appreciate. So this implies that this J2 hat is identity on K2. So what is the moral of the story? The moral of the story is when you apply these so-called, these two properties to the kernel itself, you get this beautiful thing that whenever J2 followed by something is J2, that something has to be the identity, okay? So now you apply it here. This will tell you that J2 followed by this is J2, therefore this is the identity. So the moral of the story is that, J2, so let me write it once more here. Thus, you see, J2 circle, J1 tilde circle, J2 tilde is equal to J2. This will imply J1 tilde circle, J2 tilde is actually identity on K2. And now, you can do this the other way around, and you will also get J2 tilde circle, J1 tilde is also the identity on K1. Similar kind of argument. And for that, you have to apply, the universal, the kernel property of K1, J1 to itself, okay? And what do these two tell you? These two tell you that J1 and J2 are isomorphisms, because you see J1 tilde and J2 tilde are isomorphisms because they are in opposite directions. See, J1 tilde is from, K1 to K2, and J2 tilde is from K2 to K1. And what are you getting? You are getting that both of them, if you compose, you get the identity maps. That means they are inverses of each other. So this tells you that, the two kernels are isomorphic. So this implies that, J1 tilde and J2 tilde are isomorphisms. So the moral of the story is therefore, so that is the claim. So the claim is that, if you take any two kernels, they are isomorphic. So that is why this is a good definition. And that is why the definition, the conditions of the definition are what are called the universal property of the kernel. And why it's called a universal property is because, you see, what it defines is unique up to isomorphism. Okay. So, and that is the first example of how to use a universal property to make a definition. Okay. Or the other way around, if you think a definition is good, you check whether it has a universal property. If it does, then your definition is good. Okay. So let me say this. So we call 1 and 2 above as universal property of the kernel. And how is our usual kernel connected to this? The usual kernel is gotten by, in fact, we can do more work. As I told you, you can show if you want, you can use the usual notion of kernel, okay, and check that this map J1 or J2 for a kernel K1 J1 or K2 J2 pair, these maps will be injected, okay, and the images will be normal subgroups, okay, and these are all things that one can work out. But so this is how you get it. So similarly, there are several other examples that you can work out. So I will leave them to you. So what I want to say is that you can do this, you can play this game. I did it for the kernel. Okay. Now what you can do is, you can define a universal property of a quotient, okay, of a morphism, okay, but make sure that the morphism, the image of the morphism is a normal subgroup of the target. Then you can define the quotient, okay, and then you can define the image of a morphism, and then you can define the co-kernel, okay, and these can all be defined by universal properties, okay, and so you see, once you define them by universal properties, then you've defined them in a very nice way, okay. So that's what I wanted to say in group theory. I don't want to go any further in group theory. So let's switch over to the case of vector space over a field. So let me switch over to vector spaces over a field. So so one of the important things that that one looks at, if B is a vector space over a field K, okay, then you have this so-called what is called you can always find a basis, okay. So there exists, so there's a standard theorem which says there exists a basis for V over K, and of course the way to get it is either you take the usual way to get it is that you take either there are two ways to approach it. So the basis is both a linearly independent set and a spanning set, okay. So so let me write this because I want to analyze this in the sense of universal properties. So basis is linearly independent plus a spanning set or generating set, okay. And usually you can start from linearly independent subsets and get to a basis by taking a maximal linearly independent subset, and you can get a maximal linearly independent subset using Zorn's lemma if you want, okay. And on the other hand, you can also come down from a spanning set. You can take a spanning set. A spanning set, by the way, spanning set will always exist. For the spanning set, you can take the whole vector space itself. That's a horribly huge spanning set. And then among the subsets, you can take a minimal spanning set. And a minimal spanning set will be linearly independent, so it will be a basis. And similarly, if you want to take linearly independent subsets, of course, non-zero, every non-zero vector will be a singleton linearly independent subset. So the collection of linearly independent subsets is non-empty. And then you can apply Zorn's lemma and get, a maximal linearly independent subset that will span. Okay, so that's how you get the basis. But you see, the idea of linear independence or the idea of spanning set, this involves linear combinations. So when do you say a subset is linearly independent? If any finite subset of that is linearly independent. And when is a finite set of vectors linearly independent? Any linear combination is zero, then all the coefficients must be zero. Okay, so this involves linear combinations. Okay, and similarly, if you take a spanning set also involves linear combinations. After all, the span of a subset is just you take all linear combinations, from that subset, and that's the span. That's the subspace spanned by that subset. Okay, so both the idea of linear independence and spanning set involves linear combinations. And of course, linear combinations involve elements. Okay, so this is something that involves elements. But again, if you want to, so the question is, can you make this arrow theoretic? Can you dispense with elements and just work with arrows? And so here is so let me give the motivation. So the beautiful thing is that you can define a kind of universal property, but it's not universal in one way. But it gives you the power of arrows, okay? So I will give a kind of partially universal property for a linearly independent set, and I'll give you a partially universal property for a spanning set, okay? And I will tell you why it's partially universal, okay? But it's very powerful. But you put them together, you really get a honestly universal, property, fully universal property for basis, okay? And this is usually called universal property of basis, okay? And so let me explain that. So you see, so the motivation is as follows. So what you do is that you take so example. Okay, so let me do it with spanning sets. And this idea that I'm using here can be used in after all, when you take span of a set, you are looking at the smallest subspace that contains that subset. It's a subspace generated by the subset. And this is a philosophy that you can use in various categories. So if you give me a group and you give me a subset of the group, we can take the smallest subgroup generated by that. It's called the subgroup generated by the subset. And you can also look at the smallest normal subgroup generated by the subset so that you can take a quotient. Okay. Similarly, if you are having a ring and you give me a subset, I can take the ideal generated by a subset, by that subset. Okay. And so this is a general philosophy of looking at a sub-object generated by a subset. So, so whatever I'm doing here can be adapted to other situations and other categories. So let us do this. Suppose, S inside V is is a spanning set. Okay, so what do you know? So our usual definition of spanning set is that it's a certain set of vectors, such that every vector in V can be written as linear combination of elements from this subset. Okay, that's how we normally define it. And but what are the arrow theoretic properties? So here is the arrow theoretic property. So you see, you suppose V. So you have this vector space V. And suppose W is another vector space. Of course, I'm all assuming that all vector spaces are over a field, and all maps are all vector space homomorphisms, linear maps, K-linear maps. Okay, so I'm going to do this. So you see, you have S sitting inside V. Okay, and I'm going to be very careful. Suppose that there is a suppose given a set. So I'm being very insistive here. Given a set theoretic map. And so when I say set theoretic map, why I'm insisting is because you see, this guy S is just a subset. I don't know, it's a subspace. It's not a vector space. It's just a subset. And whereas this W is a vector space. Okay. And from a subset, from a set to a vector space, I can get only a set theoretic map. If S was also a subspace, then I can think of a linear map. But you see, this S is only a set. Okay. So given a set theoretic map, let me call this as F. Okay. Okay. And suppose there are two maps, okay, from V to W, which extend this F. So I have this F1 tilde and I have this F2 tilde. Okay, F1 tilde and F2 tilde extend F. Okay, that means what? You see, mind you, F1 tilde and F2 tilde are they are linear maps. So you see, whenever I write a map from one vector space to another, it has to be linear. Okay. But from a set to a vector space or a vector space to a set, it has to be only a set theoretic map. Linear doesn't make sense. Okay. So F1 and F2 extend F. So given F and F1 and F2, of course, linear that extend F. Okay. Then then F1 tilde is equal to F2 tilde. Okay, so this is something that I mean, if you have if two linear maps, they are equal on a spanning set, then they have to be equal everywhere, and that's simply because every element of V can be written as linear combination of elements of the spanning set. It doesn't matter whether it's written uniquely or not. Okay, if the spanning set is not a basis, then it need not be written uniquely. But the point is that it is being written in terms of linear combinations of S, that is good enough to ensure that a linear map is completely determined by its value on the generators. Okay, so V has S as generators. The span of S is V. So S is a spanning set. Okay, so this is something that pretty well. Okay, now so you see, this is a property. You can see that this is a property, and and this property is the motivation for defining a spanning set. And now what has happened is you can use this to define a spanning set without using the idea of linear combination. So here's the definition. So the definition is, okay, a subset S in V is called a spanning set if this property holds. If whenever given a set map a set map F from S to W, W another any other vector space. In fact, I should not say any other, it could be even the same, any vector space. So whenever, normally we say other, but you have to be very careful in mathematics. When you say any, it could be the same thing as well, any vector space, such that and linear maps F1, F2 from V to W, such that F1 restricted to V, I mean F1 restricted to S is equal to F2 restricted to S. So this diagram commutes. Okay, so F1 restricted to S is equal to F2 restricted to S. Then it should happen that F1. So I think I put a tilde there. So let me carry it here. Then F1 tilde is equal to F2. So you see, make this definition. Okay, a subset is so spanning set means it's a subset that from that subset, if you give me any set theoretic map into another vector space, it has, if at all it has only one extension to a linear map to the whole vector space V. Okay, and you can see that if you take a usual spanning set in the usual sense, okay, then it satisfies the property of this definition. That is how I got to this definition. Now we have to prove the other way around. Suppose a subset has this property. I want to say that the subset is a spanning set. Okay, and I'll quickly indicate why that is true. Okay, so what do I have to prove? Given a subset S with this arrow theoretic property. Okay, so when I say is a spanning set here, this spanning set is undefined. Okay, I'm not using this definition. I'm just saying that spanning set means that it is arrow theoretically this has to hold, and then I have to show that it is also spanning set in this definition. So what I have to do is I have to show that if S satisfies this definition, then the usual span of S is actually V. So if this holds, okay, then span S is actually V. Why is this true? Again, you can you can see that if the span of S is not V, okay, then actually you can find a vector in V which is outside the span of S, okay, and then you can define a linear map. You can define two linear maps, okay, which are the same on the span of S, okay, and which differ on that vector outside, okay, and then that will contradict this definition, okay. Therefore, the span of S has to be all of V. So,
Balaji, you need F1 tilde restricted to S equal to F2 tilde restricted to S equal to F, right?
Is equal to F, of course. Yeah, sorry. Yeah, thank you.
Otherwise, it doesn't involve any F.
Yeah. Thank you. Yeah, F1 tilde and F2 tilde should be extensions of F. That's important. Yeah, thank you. Thank you for pointing out. That's absolutely needed. Yeah. So thank you. So therefore, you see, so now if you look at it, so I will quickly write down the proof by contradiction. If span S is a proper subspace of V, okay, what you can do is you get a basis B of inside in span S, okay, and extend to a basis for V. So let me call this as let me call the extended basis as B prime, and of course B prime is strictly containing B. That's because the span is not all of V. Okay, and what you can do is that you can define if you want two linear maps equal on span S into any other vector space, but which differ on B prime minus B. in the complement, and you contradict the definition, because these two linear maps are they're the same on the span of S. So they are, but in particular they are same on S, because S is contained inside span S, but they are therefore they are extensions. Okay, and equal on span S to, as Professor Nair pointed out, two linear maps equal on span S to, to whatever it is that F, which is that equal map. Okay. So the point is that if you have a vector outside, I can define, if it's a basis vector which is outside, then I can define a map which is different there. Okay, and so I will contradict this definition. So that is the short proof, but you can write down steps for this. Okay, so this is to tell you how you can define a spanning set. So this definition of spanning set doesn't use any idea of linear combination at all. It just uses arrows. Okay, and so this is one thing. Okay, and then similarly, you can the next thing that one can do is that you can define linear independence also in the same way. Okay, so how do you define linear independence? So let me make this other definition, and then if you put these two definitions together, linear independence and spanning set together, you get the definition of basis, and that will be a proper, universal property of. It's called the universal property of a basis. Okay, so let me say this. So the next thing, so let us look at linearly independent sets. Linearly independent sets. So you see, again, you take a vector space V and you take a set S. So suppose S is linearly independent. So if S is linearly independent, then what happens? So you see, of course, any linear combination in S of elements of S, if it is 0, then all the coefficients are 0. That's the usual definition. And what is the power of this? Okay, so there is a property that you can look at, which I have also actually used above. Okay, and actually in disguise, this is the universal property of the basis I'm again and again using. But you see, what is happening is that I'm trying to separate the two pieces, the spanning property and the linear independence property. I'm trying to separate these two ideas arrow theoretically. Okay, so you suppose S is linearly independent. Okay, then you see, you take so S is, S is a basis for span of S, and that is a subspace. That's a subspace of V. And now you see, look at what happens. See, if you given any set theoretic map, set theoretic map from S to some other vector space W, okay, and let me call it as F as usual. Okay, then what you can do is, the whole point about basis is that, which is actually the universal property of the basis, is that linear map can be completely defined only by defining it on the basis elements. Okay, so the point is that this F can be, the set theoretic map F can be extended to a unique linear map on span S. Okay, by sending every basis element in S to its image under F. Okay, so here is the picture. So you have V, you have S, and you have this W. So you have this W, that's this F. Okay, and let me put something in between. I want to put the span here. So here is the span that is sitting inside here, and the span is subspace of V. Okay, and the point is this F extends to an F tilde. F extends to F tilde, a linear map. Okay, and then this F tilde can be further, you can further extend it to, if you want, F hat. F tilde can be extended to a linear map F hat. And of course, when you want to extend F tilde to F hat, all you have to do is, you see, the S is already a basis for the subspace. You extend it to a basis of V. Okay, and then the basis of V which are outside this elements in the basis of V which are outside this S, you can prescribe F hat arbitrarily. Okay, so you can always extend. So what is the moral of the story? The moral of the story is this big deal that, from S to W, if you give me any set theoretic map, mind you, this is a set theoretic map. Okay, you can extend it to a linear map from V to W, and believe it or not, this is good enough to tell that S is linearly independent. So, so here is the arrow theoretic definition of linear independence, and where I'm not going to use linear combination at all. Okay, so here is the definition. Okay. S inside V is called linearly independent if given. So I'll put this diagram. S to W F set theoretic map into a vector space W, there exists an F hat linear map from V to W such that F hat extends F. That is, F hat restricted to S is actually F. So there is this inclusion here, and this diagram comes. Okay, and with this definition, you see, all I'm saying is that any set theoretic map from this set into any other vector space can be extended into a linear map. But watch very carefully. I'm not saying it can be extended to a unique map. I'm just saying it can be lifted to some map. Okay, and believe it or not, this is I've just proved to you that if S is linearly independent in the sense of linear combinations, this holds. But the converse is also true. If a subset has this arrow theoretic property, that from that subset to any other vector space, if you have a set theoretic map that can always be lifted to a linear map to the whole vector space, then that subset has to be linearly independent. And what is the proof for that? So the proof is, so the claim is this S is linearly independent. S is linearly independent in the usual sense. Okay, and of course, when I say linearly independent here in this definition, it is arrow theoretic. Okay, and the arrow theoretic definition was motivated by the usual definition. But I'm saying if they are equal. Okay, so you take S linearly independent in the arrow theoretic sense. I want to show it's linearly in the usual sense, and then the proof is again very, very easy, because you see, what is a proof? You have to show S is linearly independent in the usual sense. That means any finite subset of S, you have to show it's linearly independent. So what you do is that you take any finite subset and take some linear combination. If it is 0, you have to say all the coefficients are 0. That's very easy to do. So you see, take S1. So let me call it as V1, etc. up to Vn finite subset of S. Okay, suppose sigma lambda I Vi is 0, I equal to 1 to n, where the lambda i's are coefficients coming from K. There's the base field over which the vector spaces are being considered. You want to show that lambda I is 0 for every I. But then what has to be done. So you see, what you do is that you just map. See, what this arrow theoretic property says is that the moment you get a map from S into any other vector space, that can be lifted to a linear map. Okay, so it's obvious. What does a map from S to any other vector space do? It takes any V in S and substitutes it with the vector FV in the target. And if it extends to this F tilde, then any linear combination of V will also go to the same linear combination of the images in W. And all you have to do is to make a choice where the images are linearly independent. And that's very easy to do. So what you do is that you take this, S to, so you even take just this, you only take this subset, you don't have to take all of S. So you just take this subset, so I take V1, so I send Vi to Ei, okay, and what is this Ei? So I just take vector space so many copies of the vector space. So n copies of the vector space. Okay, and EI is a standard basis. And this, so this is a map from, I'm going to send it from, I'm just going to take a map from S to Kn, okay? But I make sure that the Vi go to Ei, okay, for I equal to 1 to n, and the other V's, I don't care how I map them. I just blindly map them to anything, okay? So all I need is a set theoretic map from S to Kn. Kn is the n-dimensional vector space over K. I send the Vi's to Ei's. These n V's, okay, in S. And I'm not bothered about where the other V's go. You give whatever value you want and call such a map as F. Now, by the linear independence property, arrow theoretic, what happens is that this S is sitting inside this V, and then so this is, if you call this as F, there exists an F tilde. Okay, I'm not saying it's unique. The diagram commutes. So you get F hat is linear and extends F. There exists an F hat. Okay, but now you can play this game. F hat of sigma lambda I Vi I equal to 1 to n will give you summation I equal to 1 to n lambda I. F hat of Vi is going to be Ei, that is 0, and of course this is 0 because this is the F hat of 0. I assume that this is 0. So you're getting, but the Ei's are all they are a basis. So therefore lambda is 0 for every n. So therefore this V1 etc. up to Vn, they are linearly independent. So any finite subset of S is linearly independent. Therefore S is linearly independent in the usual sense. So you see, this is the beauty of arrow theoretically capturing linear independence. Now you can put these two things together, and you can get what is called as universal property of a basis. So let me write that. So here's the definition. A subset B of vector space V is called a basis if, so let me write the diagram first. Given any set theoretic map F from B to any other vector space W, there exists a unique F tilde, which is a linear map from V to W, which extends this. Okay. Given any set map F from B to W any vector space, there exists a unique linear map F tilde such that F tilde restricted to B is actually F. Okay, and now you see, if you look at this property, the fact that any F can be lifted, what it says is that any F can not only be lifted, the lift is unique, but the very fact that any F can be lifted will tell you that B is spanning set, and any lift is unique will tell you that B is linearly independent. So B is both linearly independent and a spanning set, so it's a basis. So this is the definition of basis completely done in an arrow theoretic way. Okay? So this is another example to tell you that universal properties can be used to define things nicely in mathematics. So in fact, I had a lot of examples in mind. I also wanted to tell you about polynomial ring over a field, and I just want to ask Professor Rana if I can continue and just say that I had a lot of things in mind to say, but as you can see, I'm a pretty slow lecturer.
Professor Balaji, actually, you're not a slow lecturer. A reasonably nice speed you have catched up. But I had sort of announced it for 1 hour plus question answers.
Okay.
Some people are probably leaving because of that constraint. So
okay, yeah.
So switch over to questions and suggestions, answers.
Sure. Yeah.
That will be a more. So if you like to conclude, you can please go ahead.
Yeah. So I just wanted to say that there are so I wanted to give this example of polynomial ring over a field. And the problem is that when you define polynomial ring over a field, the catch is that you say, let x1, x2, etc. be variables or indeterminates, and then you start defining polynomials in x1, x2. Okay, But then the problem with this definition is, what is this x1, x2? Okay, you say they are indeterminates, they are variables, but what is the meaning of indeterminate? What is the meaning of variable? That's not properly defined. Okay, and so this is a big catch in the definition of the polynomial ring itself. And I wanted to say that if you use what is called universal property of the polynomial ring, which is actually a concept of what is called as algebraic independence over field, then you can use the same kind of arrow theoretic definitions with universal properties can be made to give a clean definition where, I can define polynomial ring without using the word polynomial, without using variable or indeterminate. And, therefore, this, you don't have to go around in circles to go back and define what is meant by a variable or an indeterminate. So that was one important example I wanted to discuss. So that is one thing. And then I also wanted to say that, there are examples in topology. For example, in topology, if you take subspace topology, okay, or if you take quotient topology, or if you take product topology, these are all given by universal properties. For example, completion of a metric space is given by a universal property. The 1-point compactification is given by a universal property, okay? And stone check compactification also comes from with a universal property. So universal properties are they are quite ubiquitous in topology. And also there are several examples in analysis and manifold theory where universal properties come. So I just want to say that these universal properties are they are ubiquitous. They are everywhere, and there are lots of books. You can look for books they are called books on universal algebra, and there are lots of books now which deal with these kinds of things. And you have a lot of material on the internet, so people who are interested can go further, and explore these ideas. Yeah, so I think I'll stop here. Though of course I would, I have probably a bad reputation of not willing to stop at all, and it's there. So
yeah. So let me request people to. You have already given some hint about references. Somebody had put a question that, can you please give some references of some books, particular books on category theory? So if you want to say something about that, you already mentioned on internet.
Yeah, I think you. There are several. If you just Google category universal properties or universal algebra, as it is called, there are lots of books there are books with even titles which say universal algebra. There are lots of books, and in fact, one of the, I would say, for masters and PhD students, one of the nice things is, for example, I would recommend to take Lang's book, Lang's Algebra, which is my favorite. And there, several universal properties are explained, categories, functors are defined. They are explained very nicely, and one can look at that. And of course, nowadays, all this stuff is available in so many places in the internet. Feel free to, just you ask Google and you immediately see entries in Wolfram Math World or MathWiki or Planet Math or EIMS, Encyclopedia of Mathematical Sciences. So a lot of stuff is available.
Yeah, I see the problem with Google is it gives a lot of stuff, but it doesn't tell which could be a good one from some point of view. So probably the audience want to know from your point of view. You said Lang is one good reference book.
Yeah, so I think there are the universal properties. One good reference is Lang, and then just hold on. I think in commutative algebra, for example, you have, or even in algebra, you have universal property of tensor product, you have universal property of direct sum, and then you have universal property of localization. So there are these kind of things are covered in, for example, Atiyah McDonald's Introduction to Commutative Algebra, which is a standard book. That's one more book that you can look at. But if you just hold on for a moment, let me stop sharing my screen and let me look at this reference. Just hold on. So I think there was a book that I had in my just hold on.
Yeah, please go ahead. In the meantime, anybody else would like to say some comment or suggestions or additions to what Professor Balaji said? Nair, you want to say something?
No, I just wanted to appreciate. I think he has explained very clearly the categorical notions, how it can be used for, defining in terms of illustrated through basic whatever properties or bases, as well as the first part, the quotient and all those things. So it's nicely presented, so that people can start any other book and then start with this background. It will be more familiar, so that you can continue to learn such properties in other contexts. Yeah.
Professor Shastri, I saw you joining. Are you there? Professor Shastri, would you like to add something? Say something?
Hello.
Please. Yes, welcome. Would you like to say something?
I would request him to at least take another 2 minutes and tell me exactly what is the definition of polynomial ring. It was in the title, it was in that one, but he didn't get time for that.
Yeah.
Just give the definition from the point of view of arrows.
Okay.
And let the audience figure out the rest of it, because it's too much of time already.
Yeah.
But Venkata should at least tell that much, just to complete his own title.
Okay.
Yeah.
Sure. Yeah, I would love to do that. Yeah.
Yeah. Professor Balaji, can you just complete the definition of polynomial rings via function?
Yeah, I'll do that. Thank you, Professor Shastri. It's again honor. I remember all the AFS that we used to enjoy conducting and lecturing in, and I hope it's revived. So so let me quickly finish this definition. Definition of polynomial ring over the field, say, in the variables S. Okay, so so this is the definition. So given Ks, this is a symbol, is so let me say the following thing. So it is a ring. It is a K algebra A with S subset of A, such that given any, so I have to say that so the category that you are working in is the category of commutative K algebras, and this is the category of the objects are all rings which are also vector spaces over K. Okay, in a nice way. Okay, so that the vector space multiplication and the ring multiplication behaves well. And the homomorphisms are K algebra homomorphisms, which are both not only ring homomorphisms, but they are also K linear maps. And so that is a category of commutative K algebras. And in that category, K algebra A and a subset S, which we will call the subset of variables, and A, the polynomial algebra over K with those variables S, is one that satisfies the following property, says that given any set theoretic map, so S to B, B any commutative K algebra, given a set map F, there exists a unique K algebra homomorphism from A which extends this. Which extends A. So this is the definition. And then this subset S is called set. Every element of the subset S is called a variable or indeterminate over K, and A is called the ring of polynomials over K in these variables given by the elements of S. So this is the definition. So it's an exercise to check that that actually S generates A, okay, as an algebra. That means every element of A can be written as a polynomial in the elements of S with coefficients in K. So S generates A as a K algebra, and you can also check that the elements of S are algebraically independent from this definition. So the moral of the story is that actually when we define a polynomial over a set of variables, we are careless about defining the idea of variable, and variable means that it can take on any value. That means you can substitute a variable with any other value. Now this power of substitution is what is being highlighted here. This F is the substitution. You are sending every element of S to a certain element in B, and that is arbitrarily done. So that's the power of a variable. You can just plug anything there and lift it and do this in such a nice fashion so that it respects scalar multiplication, vector multiplication, ring multiplication, and that's how you get this F tilde. So this power to make the variable take on any value, that is what is actually in a sophisticated way given here. Okay, so I think I'll stop with that.
Sir,
Yeah.
that is why this is sometimes called the evaluation homomorphism, right? The evaluation map.
Yes, exactly, that's right. F tilde is the evaluation of S, every element X in S with F of X. Yeah, it's a substitution or evaluation. That's correct.
So do you actually require this S to be a subset of A, or any inclusion will work?
Well, actually, the truth is that you can have if you want to be more, you can even take a map from S to A. You can just take a set S and then you can take a map A. I mean, and you can take an algebra A, and S to A can just be even a set theoretic map with this property. It will follow that this map has to be injective. And it will also follow that A will be generated by the image of S. Yeah, in fact, I don't have to even say that. So this is there are certain things you can remove.
Yeah.
You can check this down. You can check this.
From
I mean, if S to A, if you have a map, you could have you can check that you can just work with the image of the map, which is a subset of the target, and replace it by an inclusion.
Mr. Shastri wanted to say something, and
Yeah. This is very much similar to the definition he has explained so painfully of vector spaces over S.
yes, I agree.
So this is one step ahead. If you change the category, the same definition gives you different objects. This is the point. There you just take vector spaces and linear maps. Here you take algebras and algebra homomorphisms. Okay, so the same definition gives you various sort of, that is the universal property of the universal properties. That's what I wanted to say.
Yes, very well explained, Professor Shastri. Yes,
Yeah,
I agree.
that's beautifully said.
However, there is one point in all this, namely existence.
Yeah, that's another story I have not told about.
You may make many definitions, but there are categories wherein existence doesn't hold.
Yes.
Okay, so existence actually in practice, what we have is you have constructions, constructive prose. That construction is taken as definition in the usual way. Like, when you say vector space generated by this one, you take finite combinations of linear combinations of elements there and so on. So that is the construction.
Sure.
Okay.
Yeah.
Quite often you
Yeah.
can many things which you can just do by this universal property without bothering about the construction. But I want to warn you, there are cases wherein there is no proof using the universal properties. You have to go to the construction. This happens especially with the free groups.
Yes.
I just wanted to ask Professor Shastri at this stage and Balaji, does it relate with the basic set theory saying that you have to assume axiom of choice and well-ordering principle and such things?
Pardon me, can you again repeat that?
See, saying that a constructive approach normally works only when there is an axiom of choice assumed, right?
Yeah.
Often, yeah, you are right.
All these things, I think, will work only wherever construction comes into picture. One has to say that, one has to categorically mention that you are using axiom of choice.
That's true. You the axiom of choice, for example, is equivalent to even Tikhonov's theorem, which is a very deep theorem in topology. So axiom of choice, without axiom of choice, you cannot do anything.
Yeah, that's right.
Yeah. For example, if you take two bases to begin with, I cannot even without axiom of choice, I cannot even say that it should be true that one has cardinality less than the other.
Right. Yeah.
Less than or equal.
Yeah.
Agree.
In modern algebra, heavily both algebra and topology, even measure theory, heavily depend upon axiom of choice.
Yeah, axiom of choice. So I think let me ask audience if they have anything to ask, because we can always interact on the email and other things. Yeah. But if the audience have something to ask, add on.
Yeah, hello, sir. Sir, in the definition of span and basis, sir told that it is a partial universal. So what do you mean by, sir, partial universal?
No, partially universal means that, in the sense that, for example, universal property should define something uniquely. So if I define a spanning set, spanning set is not unique, right?
Yes, that's correct.
So from that definition of spanning set, I cannot say that, two spanning sets are in some way related. I cannot say that. Similarly, if you take two linearly independent sets, how they may be related, I cannot say. That's why I said it's kind of partial. But if you put both together, you get bases. Then any two bases are bijective is a theorem.
Change of basis.
For uncountable cardinalities, this certainly uses comparing cardinalities, which is a consequence of axiom of choice, without which you cannot compare two cardinalities. So only if you take universal property of basis, you can say that two bases are the same. They have the same cardinality. But then if you take only the definition of spanning set or linearly independent, that's not kind of universal in that sense. There's nothing universal about a spanning set, except that, the power of arrow theory makes you to define everything using arrows. That is the point I wanted to say.
Okay.
Sir, how to connect two bases using the universal property of basis of a vector space?
No, that is a proof that is a proof that you'll have to do. Given any two bases, you have to show that there is a bijection.
Yeah, no, I was asking because in your definition, there was no apparent map between two bases of a given vector space.
No, that requires more work. One has to, as Professor Shastri and Professor Rana were saying, somewhere axiom of choice will come in. You have to take these two bases, and then, then you have this the comparability axiom that, any two cardinals, one of them is less than or equal to the other. And what you'll have to show is that, if one of them is less than or equal to the other, but it is strictly less than, you have to get a contradiction. But what is, of course, if it is finite or something, you can do it. But if it is infinite and uncountable, for example, then you will, if the cardinality of one basis is strictly less than the cardinality of the other, you can arrive at a contradiction. Some more work needs to be done. Yeah, it's not obvious.
So it is not a purely consequence of the universal property.
No, not directly. So somewhere the axiom of choice will, it will come in and it will create, without that you cannot do it. Because you see, after all, I said we are starting with set theoretic maps. Okay.
Yeah.
So at some point you want existence of set theoretic bijection between two bases, and that has to be chosen in some way, or the moment this comes, axiom of choice or well-ordering principle, Zorn's lemma, and axiom of comparability, all of these things in some form will enter, without which you cannot deal with infinite cardinalities.
Yeah.
It's not obvious. It's not obvious from this.
I see Professor Ravi Kulkarni is there. Would you like to?
Yes, hello.
Hi. Would you like to say something, add a comment, or?
For instance, every vector space has a basis, but that basis may not be constructible in some sense.
Yes.
This question comes up when you ask for a basis of the real numbers over the rational numbers.
Yes. Okay.
Yes. I always put it like God exists, but you cannot exhibit it.
Very good.
So it's a matter of faith.
Yes, matter of faith. Whether you believe in God or you don't believe in God, it's your choice.
Yeah, mathematically, faith is just axiom.
Yeah, that's right. Among the audience, anybody has a question to ask related to the topic from the speaker? Please.
Sir. Sir.
Yeah.
Krishna.
Sir, yes, sir. Sir, while defining the linear independence by means of the universal property, was the uniqueness of the map F hat assumed, the uniqueness?
Yes. No, for linearly independent, you don't need the uniqueness of the map. You can just extend.
Sir, we don't need to have the uniqueness of F hat.
No, you will not have, because you see, if you had uniqueness, then it will not just be linearly independent, it will also span, it will become a basis. Then and only then you will get uniqueness.
Sir, then how does the uniqueness come up while defining the basis from?
No. So you see, this is it's all boils down to this often repeated sentence that to define a linear map, you have to only define it on the basis. Defining a linear map amounts to only telling what is the image of every basis element under that map.
Yes.
So that set theoretic map from the basis to the target vector space, which sends every basis element to a target vector, that completely determines the linear map. And that is essentially the universal property of a basis. And so this involves two things. It involves, first of all, the linear map should be extended. The set theoretic map should be extended to a linear map, and it should be extended uniquely. If you separate this out, that it can be extended, though not necessarily uniquely, that is the linear independence part. On the other hand, whenever it can be extended, if it can be extended only in a unique way, that is the spanning part. So if you put them both together, you get basis.
So in case when we don't have a unique extension, what problem might arise then in that case?
I think Krishna will not enter into discussion. If this, then what will happen? That you should communicate with the Professor Balaji over the email with more elaborations on possible cases, right?
Yes, sir.
Yeah. So Balaji, can you share your email where people can communicate with you?
Sure.
You can either write it in your screen, or that is good enough.
I can write it here. So it is tbal@iitm.ac.in. Yeah. So
thank you.
You're welcome to.
You are welcome to communicate. We mathematicians always are happy that if students ask questions, and we try to respond.
Sure. So I also look forward that if I get another chance sometime, a slot, then I would like to also give some more examples involving topology, of universal properties, and say more about categories and functors, which I couldn't come to.
I think Balaji, you are already giving me ideas. that I can rope you in. Thank you for indication. We will positively do that.
It's a pleasure and honor.
Yeah, where some more specialized things can be discussed, because I wanted some overall picture to be given. You have given it very nicely by giving examples of vector spaces and groups, how universalization of universal properties gives rise to better understanding of various things. So more in-depth series, I'm also thinking of requesting people to give some in-depth talks. So there, I think a talk by you will be a very useful one. So I think it's already almost 2 hours since we started. So
Sir?
Yeah, somebody has a question. Yes, please say your name.
Sir, I am Divya and I want to share my experience. Can I?
Yes, please go ahead.
Sir, actually, 1 year ago, I appeared in an interview and I was asked a question related to vector space. Can we define basis in the sense apart from like we define minimal spanning set and maximal Li set? And from past year, I was in search of the answer of that question. And today, I can say that my struggle ends. Thank you so much for this session.
You're welcome. You're welcome.
Okay, thank you very much. I think with this positive note that our clinic, math clinic talks are really helping to clean out some doubts in the minds of the audience. Thank you, Balaji, for your presentation. It cleared my doubt, which I wanted to ask that, and Shastri added to that, that there is a universal thing about the universal properties. Thank you very much, everyone, for participating in this talk, and hope you will keep coming back when as and when we announce more talks. Thank you and take care. Thank you.
Thank you, Professor Rana.
Yeah, thank you, Soumya, for the background help. Okay.
Thanks a lot.
Yeah. Bye. Take care.
Bye. Thank you. Take care, everybody.